I'm your host, and today we're moving into the very heart of how we design and understand intelligent systems in the embodied cognitive science framework. Our deep dive today covers chapters 10 and 11 from part 4 of Understanding Intelligence by Rolf Pfeifer and Scheier, a section dedicated to the core principles of intelligent systems. Last time, we explored how artificial evolution and dynamic systems offer powerful ways to generate and analyze complex behaviors. But as we transition from what intelligence is to how it's built, a crucial question emerges. What are the fundamental guiding principles that allow us to design truly intelligent, adaptive agents that can thrive in the complex, unpredictable real world, moving beyond the limitations of traditional, centralized approaches? Part 4 of the book, Principles of Intelligent Systems, attempts to answer this by integrating all the insights we've gathered so far into a coherent theoretical framework. Chapter 10 lays out a set of design principles for autonomous agents. These aren't just abstract ideas. They're practical heuristics or guiding rules for building agents that exhibit rich, diverse behaviors rather than just executing pre-programmed sequences. The authors start with a meta-principle, a principle about principles themselves, the three constituents principle. This states that any intelligent agent design must always consider three interconnected elements. First, the ecological niche, which is the specific environment the agent will operate in. Remember, there's no universal agent in the real world. Every agent is designed for a particular context, and exploiting that context's constraints can simplify design. Second, we define the desired behaviors and tasks the agent should perform. And third, we design the agent itself, its body, its sensors, its internal mechanisms. Building on this, Chapter 10 introduces several agent-specific principles. The complete agent principle emphasizes that intelligent agents must be autonomous, self-governing, self-sufficient, able to sustain themselves, embodied, physical entities in the real world, and situated, perceiving the world from their own perspective. These are the hallmarks of true intelligence. The principle of parallel, loosely coupled processes is a cornerstone. It states that intelligence emerges not from a single central brain, but from many parallel processes running asynchronously, directly connected to the agent's sensors and motors. This is a direct challenge to the traditional sense-think-act cycle of classical AI. The principle of sensor-motor coordination tells us that perception, categorization, and even memory are fundamentally intertwined with sensory and motor processes. Agents don't just passively receive information. They actively interact with their environment to structure their own sensory input, which simplifies learning and grounds meaning in their experience. The principle of cheap design encourages parsimonious, or simple, designs that exploit the physics of the environment and the constraints of the ecological niche. The redundancy principle suggests incorporating overlapping information channels in sensors, not just for robustness, but crucially, for generating behavioral diversity. The principle of ecological balance states that the complexity of the agent, its sensors, motors, and internal mechanisms, must match the complexity of its task environment. Finally, the value principle highlights the need for an internal value system that guides self-supervised, incremental learning, allowing the agent to judge what's beneficial. These principles are not isolated. They are deeply interconnected, forming a coherent story about how intelligence arises from the dynamic interplay between an agent and its environment. Chapter 11 then takes a deep dive into the principle of parallel, loosely coupled processes. This principle directly confronts the traditional hierarchical view of behavior control, which often assumes a central planner dictating a sequence of actions. Think of the old test operate test exit or TOTE model in psychology, or the STRIPS planner in early AI. These models relied on a top-down sequential control. The embodied approach, however, argues for a different way of organizing an agent's internal processes. Instead of functional modules, we define parallel processes that are directly connected to the agent's sensor-motor apparatus. These processes need to be coordinated either competitively, where one process takes precedence, like in the subsumption architecture we discussed last time, where a higher layer suppresses a lower one, or cooperatively, where the outputs of multiple processes are combined, often through summation. Crucially, this coordination often emerges from the agent's interaction with the environment itself, rather than being explicitly managed by a central controller. The chapter illustrates this with several architectural approaches. A process description language, PDL, where multiple processes continuously contribute to motor commands, and their combined effect determines behavior. Action selection dynamics, where behaviors are activated by internal motivations or external perception, and then compete for execution. The extended Bratenberg architectures, EBA, which generalize Bratenberg's simple designs into more complex systems where many simple, pre-wired processes run in parallel, and their combined output drives the agent's actions. This approach finds support in neuroethology, studying how insect motor systems and even human visual systems operate through parallel, distributed loops. The immunoid approach uses concepts from the biological immune system, where sensory inputs are like antigens and internal processes are antibodies that compete to respond to the current situation. Even collective approaches for groups of robots demonstrate this principle, with emergent cooperation arising from simple, local rules between individual agents. To truly bring this to life, Chapter 11 presents a fantastic case study. A self-sufficient garbage collector robot designed using the extended Bratenberg architecture. This robot incrementally adds processes. One for moving forward, one for avoiding obstacles, another for going to a charging station, and one for recharging. The robot's ability to grasp objects, for example, isn't explicitly programmed. Instead, it emerges from the interaction of its move forward and avoid obstacle processes with the specific shape of its hook and the objects in its environment. Even more strikingly, the robot exhibits what appears to be rational behavior. When its battery is low, it stops grasping objects and prioritizes heading to the charging station. This isn't a result of complex planning, but an emergent outcome of the parallel processes, where the go-to-charging station process's influence on motor speeds increases, overriding other behaviors. This demonstrates how self-sufficiency and complex, goal-directed behavior can arise from decentralized control. So, to answer our question, the fundamental guiding principles for designing intelligent, adaptive agents in the real world involve a radical shift from centralized control to parallel, loosely coupled processes. Intelligence is not just about what's in the brain, but how the entire complete, embodied, situated agent dynamically interacts with its ecological niche, guided by a set of interconnected design principles that foster emergent, adaptive behavior. That concludes our deep dive into chapters 10 and 11. In our next episode of Deep Vices, we'll continue to explore the fascinating world of brain, mind, and intelligence as we delve deeper into the principles of sensor-motor coordination, cheap design, and the role of value systems in shaping intelligent behavior. So, stay tuned.